Welcome to the Deep Dive. Today, we're digging into a really neat puzzle in AI. It's all about how we get these large language models, these LLMs, to actually reason through complex problems, step by step, kind of like how we might tackle something tricky. And we've got some pretty cool research to unpack that aims right at this challenge.
Yeah, exactly. And a big piece of that puzzle is feedback. How do we tell these models if they're on the right track when they're learning to reason? Generally, there have been like two main schools of thought here.
Okay.
First, you've got outcome-based rewards. Simple idea. You just look at the final answer. Is it right? Is it wrong? That's it. It feels pretty intuitive, and honestly, we've seen some really impressive results using this approach.
Right, but it sounds a bit like getting your final grade on a big project, but no comments along the way.
Uh-huh.
If the final answer is just wrong, how's the model supposed to figure out where it messed up? Like, which step in its thinking went off the rails?
That's precisely the problem. It's called the credit assignment problem, and it's tough. Plus, learning can be really slow, right? If you only get that thumbs up or thumbs down way at the end.
Okay, so that's one way. What's the alternative?
The other main approach is procedure-based rewards. Here, you give the model feedback after each step it takes. Think of it like a coach guiding you through every single move.
Ah, okay. That sounds much more efficient for learning. The model gets instant guidance.
It absolutely can be. Much faster learning, clearer signals.
Sense a but coming.
There's always a but. The huge hurdle is, well, who provides that step-by-step feedback? It usually needs a massive amount of human oversight, defining all the right intermediate steps, checking the model's work at each point. It's just not very scalable for these huge, complex models.
Right, doesn't seem practical for real-world training. Okay, so we've got this trade-off.
Yeah.
Outcome-based. Great results maybe, but slow and fuzzy on why something failed. Procedure-based, efficient learning, but needs way too much human hand-holding.
Exactly. And that sets the stage perfectly for the research we're diving into today. It's from a paper called Reasoning Without Regret. The authors are essentially trying to get the best of both worlds. How can we get the power of outcome rewards with the learning efficiency you get from step-by-step feedback, but crucially, without all that intensive human supervision?
Reasoning Without Regret. I like that title. Okay, so they introduced this framework, BARS, Backwards Adaptive Reward Shaping.
That's the one, bars.
And they call it a no-regret framework. Sounds promising, very efficient. So how does it actually work? What's the magic here?
Well, the core idea behind bars is pretty clever. It basically takes those simple, sparse rewards, just the final correct or incorrect, and finds a way to translate them into more useful procedure-like signals after the fact.
Okay. How does it do that translation?
Think of it like this. Imagine you bake a cake, and it tastes awful. You only know the final outcome. Bad cake. Bars is like trying to intelligently figure out, just from that final taste, which ingredient you added way back at step 2, or maybe which cooking step was the most likely reason it went wrong.
Ah, okay. So it's inferring the step-level feedback from the final result. Without someone needing to taste the batter, check the oven temp constantly.
Exactly. And the absolutely key part is, like you said, doing this without needing step-by-step human feedback during the process. That's the potential game changer.
Okay, that's intriguing. How does it technically pull that off? The paper mentions some specific concepts.
Right, so it uses something called sparse rewards generated from terminal state priors. Let's break that down a bit. A terminal state is just the end result, the final answer. The priors are sort of the model's initial best guesses or beliefs about what a good final answer should look like, even before it starts reasoning.
Okay, so it has some expectation of the destination.
Kind of. And then it uses these initial guesses about the end state, combined with the actual outcome reward, to work backward. They also use a technique involving something called cover trees.
Cover trees. What do those do?
They're a data structure, basically a smart way to organize the possibilities. In bars, they help to effectively scale the rewards and, importantly, prevent something called exploitation.
Exploitation. You mean like the model finding a loophole, a trick that gets the right answer sometimes, but isn't actual solid reasoning?
Precisely. You don't want the model just latching onto some simple trick that works for a few examples but doesn't generalize. The cover trees help ensure the learning process explores different reasoning paths properly, efficiently, without getting stuck down one potentially flawed path. It encourages broader, more robust learning.
Gotcha. So it keeps the learning honest in a way. Now, the paper also dives into some fairly heavy math to back this up, right? Things like Bellman contraction and Japra.
Yeah, the theoretical foundations are quite rigorous. You don't need to be a math whiz to get the gist, though. Think of Bellman contraction as a guarantee that the model's estimates of how good certain steps are will eventually settle down and converge towards the true values. Like focusing a lens, it gets sharper and clearer over time.
Okay, so it ensures the learning process is stable. It actually gets somewhere reliable.
Exactly. And the gap rewards relates to how distinguishable the best path or action is from the next best ones. If there's a clear gap, a clear winner, it's easier for the model to learn the optimal strategy.
Makes sense. A clear signal is easier to follow.
Right. And based on these mathematical underpinnings, they can actually provide guarantees about bars' performance.
Guarantees. Like what?
They show that bars can reach a certain level of accuracy, call it accuracy, pretty quickly within a specific number of iterations, which depends on factors like that reward gap. And maybe even more importantly, they talk about no regret, specifically log T dynamic regret over $2 rounds.
Okay, and dialogue regret, what does that mean in plain English?
It means that over a long period of learning $2 rounds, the model's performance doesn't fall far behind the best possible strategy it could have learned in hindsight. It learns efficiently and doesn't keep making suboptimal choices repeatedly. Its cumulative mistakes grow very, very slowly over time.
So it learns fast and it learns well, sticking close to the optimal path without constantly second-guessing or halving.
Right.
Well, regrets.
That's a great way to put it. Efficient and reliable learning.
That does sound significant. And they connect this theory back to practice.
They do. The authors use some pretty advanced analytical tools, things like generic chaining, scaling limits, Feynman-Cac bounds, quite sophisticated stuff. But the point is, this analysis helps bridge the gap between this new theoretical framework, Otter errors, and the recent empirical successes we've seen with models trained using primarily outcome-based rewards.
Wait, so this isn't just theory. This math actually helps explain why some of the really powerful AI models out there, the ones making headlines, might be working so well, even though they were trained mostly just on final answers.
That seems to be the implication, yes. Their work provides a solid theoretical foundation to understand why those simpler outcome-based methods can, under the right conditions or with the right implicit structure, be surprisingly effective. And they specifically point out that bars is essentially the first rigorous, proven, no-regret algorithm for this kind of outcome reward shaping. They even suggest this offers a theoretical grounding for the empirical success observed in models like DeepSeek's R1.
Wow. Okay, that connection is huge.
Yeah.
So ours isn't just a proposal for a new way to train models. It might actually be shedding light on why some current state-of-the-art models are already so good.
It potentially does both, yeah. It provides a new, efficient algorithm and a deeper understanding of related existing successes.
So if someone's trying to wrap their head around this, what's the main takeaway message?
I think the key thing is that bars offers a really clever way forward for training LLMs on complex reasoning tasks. It lets us leverage the simplicity of outcome-based rewards, just checking the final answer, but injects the efficiency you'd normally associate with detailed step-by-step feedback without needing all the human labor for that feedback. It's potentially a way to get more capable, more efficient AI reasoning systems faster.
Okay, let me try to sum that up. BARS is this framework that cleverly turns end result feedback, which is easy to get, into something that guides the learning process almost like step-by-step feedback would. It does this using some smart math and structures like cover trees, crucially without needing a human to look over its shoulder at every step.
Exactly.
And the potential benefits are faster learning, better identification of where the reasoning went wrong, and, fascinatingly, it also gives us a stronger theoretical handle on why some existing AI methods, like maybe those used for DeepSeek R1, have been working so well.
You got it. It's a really nice blend of theoretical insight and practical potential. It highlights that sometimes understanding the why behind AI success is just as important as achieving the success itself.
Absolutely. Which leads to maybe a final thought for our listeners to ponder. Considering bars is all about reasoning without regret, learning efficiently, and minimizing mistakes, how could that core idea apply to us? How might you, in your own work or learning, approach complex problems to minimize missteps and optimize your path forward, even if you don't have constant feedback at every single stage? Something to think about.
It's a great question, and for anyone who wants to really get into the nitty-gritty of the bars framework and the math behind it, the paper Reasoning Without Regret is up on arXiv. The identifier is arXiv.2504.09777.
Perfect. Thanks for joining us on this deep dive. We'll catch you on the next exploration.